This video lecture is meant to cover the information found in 9.2 Hess's Law. This was not in Rosengarten. Hess's Law, you want to be able to harvest the information from your reference tables. There's two reference tables, both show enthalpies. AE reference table B shows you heats of formation. Heats of formation basically is just showing you the energy either absorbed or released when you form 1 mole of the substance, so therefore the unit is in kilojoules per mole. Reference table I shows you the heat of the reaction. It shows you however much energy is absorbed or released for the reaction as it is written. So it's not necessarily per 1 mole of product. So therefore the unit on table I is just kilojoules. Now if you're given an equation and asked to determine the energy released or absorbed, and I've given you different quantities that are shown in the coefficients of the balanced equation, what you'll want to do is use a proportion. So if we have this example, we have nitrogen N2 plus 3H2 turning into 2 moles of ammonia, and delta H, you look it up on table I, and you find that it is negative 91.8 kilojoules. Negative means it is exothermic, so we need to find out how much energy is released, not when 2 moles of ammonia are formed, as shown in the equation, but when 5 moles of ammonia is made. So to do this, you would want to use a proportion, effectively. So let's see about, I can push this page up a little bit. Okay, so what you would want to do is that you know that 2 moles of ammonia produced will release 91.8 kilojoules. So instead of 2 moles, what about 5 moles? Equals to x. So this is just now a cross multiplication. You know, 2x is equal to 5 times negative 91.8. Divide all of that by 2. And of course, this is not mental math, so we would have to do this quickly on your calculators. And let's see, if we have 5 times 91.8, divide that by 2, we get 229.5. So let's call that to 3 sig figs. We would have to say that x would be equal to, let's see, it's a negative number, negative 230. And that's in kilojoules. Okay, so that's how you would solve that type of a problem. Now, if you are given 2 to 3 equations, and then you are asked to find the delta H of the reaction for a target equation, that target equation will be a sum of the 2 to 3 given equations. So to do this, you either flip or you don't flip the given equations to try to match the target equation. If you flipped the equation, you will change the sign of delta H. If you did not flip the equation, you leave the sign of the delta H as is. You then cancel out terms that show up on both sides of the equation. You rewrite the equation as it should add up to the sum of the target equation, and then you add up the delta H's to find the delta H for the reaction. So here's an example. If you're being asked to calculate the delta H of a reaction for 2C plus O2 turns into 2CO. So this right here is our target equation. This is what we're trying to make our given equations match up to this. You're given C plus O2 turns into CO2 with a delta H of negative 394 kilojoules. You are given 2CO plus O2 turning into 2 CO2s with a delta H of negative 283 kilojoules. I'm going to push up this equation so we can do our work down here. Now, what we want is to keep the carbon right here on the left side of the equation. We want this to stay on the left side of the equation. Now, in our given equations, the only place where I see carbon alone is in the first equation. Okay, so I'm going to write the 2 arrows to represent the 2 equations. I'm going to keep this first equation as C plus O2 turning into CO2. And I'm going to leave the negative 394 as is. The second equation, what I need to do is I need to get the carbon monoxide. This is the only place where carbon monoxide shows up in my given equations, but in the target equation, it's on the right side. So I need to flip that equation so it reads 2CO2 on the left side and 2CO plus O2 on the right side. Now, since I flipped that equation, I have to change the negative 283 to a positive 283. All right, Now we need to start canceling things, but it looks like we will need to double the first equation. Okay, why do I need to double the equation? Well, given right here I have one carbon here, but I need two carbons. So let's try doubling this whole first equation, in which case when you distribute it through, you're going to have two carbons, two O2s, and two CO2s. So I'm going to get rid of that too so that doesn't confuse us. And then we need to double this right here. So 2 times 394 is going to give me 788, negative 788. Okay, so now let's take a look at what happens. I see that there's two CO2s. There's a 2 CO2 on the right side, there's a 2 CO2 on the left side, so those will cancel. Now I have 2 oxygens on the left side right here, and 1 oxygen on the right side. So we need to cancel this one O2 with one of these on the left side. And I believe that should give us our target equation. If we rewrite this, we'll get 2C plus O2 turning into 2CO, which is indeed our target equation. So that means we just need to add up the values over here. So negative 788 plus 283 leaves me with a negative 505 kilojoules. So that right there is our heat of our reaction. All right, let's take a look at the problems in the problem set. All right, so this is question number 10. How much heat in kilojoules would be released by the complete reaction of 2 moles of H2 in excess N2? So what we see is this equation. It's the ammonia, formation of ammonia equation. It is a negative 92.4, which I now realize is a slightly different number from what I showed you in the example. So I had one source that's more accurate than the other, but we're just going to go with it. So we see that we have 3 moles of H2 will give us negative 92.4 kilojoules. But we're talking now about 2 moles, so we need to set this up as a proportion. So 2 mole of H2 is going to give us X. So here it's just a matter of cross multiplying. We get 3X is equal to 2 times negative 92.4. Divide that by 3, and we should get that X is equal to negative 61.6 kilojoules. So that gives us that nice answer right there of choice B. All right, let's take a look now at the next question. Given the following at standard conditions, we have 2 given equations, and it says to find the delta H for the reaction below its standard conditions. So this right here is our target equation. It's our target, and we have these 2 givens. So if we rewrite these 2 givens like so, let's see, in our target we have the IF5 on the reaction side, but the only place we see IF5 is in the second equation, so we're going to need to flip that second equation. So IF5 turns into IF plus 2F2. And if we flip that, then that means we have to change that sign to positive 745. Now, if I leave the first equation, I think we're going to need to leave that first equation as is because the F3 is on the right side, and that's where it is in the target equation. So IF3 on the right side, and on the left side of that equation is IF and F2. So since we're leaving that equation alone, we're going to leave that as negative 390. All right, so let's see what's canceling. Anything canceling? So, well, we've got the IF on both sides, so that's gone. We have one F2 on the left side and 2 F2s on the right side, so we're going to get rid of the 1 F2 on the left and one of the 2 F2s on the right. And then I believe if we just draw everything, bring everything else down, we've got our target equation. IF5 turns into IF3 plus F2. So now it's just a matter of adding up those 2 numbers, negative 390 plus 745, which should give you a positive 355 kilojoules. All right, that's it for Hess's law. We'll see you back in the classroom for the next section.